let's talk about the substitution rule with definite integrals. So you can definitely compute definite integrals with the same methods that we have been doing substitution with. So we can just follow our exact same process. At the end, substitute our u back in, come up with our capital F of x, and evaluate it across the interval from a to b. But we can also do what I've got written down here. If we happen to have a definite integral, when we make the substitution for u of x, and then make the substitution for du, we can also make the substitutions on the bounds. And sometimes that can be helpful, that can shortcut our work, or, I don't know if it shortcuts our work, it's just a different way to do our work. But if we do that, then we can actually just do the evaluation across u rather than going back in terms of x. So then we can find that we have f of u, and we can evaluate that from u of a to u of b, and we never have to go back in terms of x, and that can be useful. So let's do a couple of examples and show what that would look like. So again, just as a reminder, I just threw these steps back up again because we're doing substitution. We're using definite integrals in our examples here on this video, but we're still just doing substitution. So we'll determine our u, we'll find our du dx, and then separate the differential and find du, and then we will make the substitutions, integrate with respect to u, and then simplify. This is the part right here where we don't necessarily have to back substitute if we have a definite integral. So it's step 5 that's going to be a little bit different in these definite integrals, because I'll show you how we can also change the bounds if we don't feel like back substituting. So let's take a look at this guy. We've got the integral from 0 to 1/2 of inverse sine of x over the square root of 1 minus x squared dx. And we want to find our u to start off with. So we're looking at this, we're thinking that's definitely not a basic integral strategy, but I do see this sine of x, and I see, let's rewrite this so that we can look at this in one other way. So I'm looking at that and I'm thinking, okay, this is the inverse sine of x times 1 over the square root of 1 minus x squared dx. And again, you might not need to, I'm going to go ahead and write that this is x equals 0 and x equals 1/2. So again, we're going to be making some substitutions, so we want to remember what our bounds started as. They were in terms of x when we started. Those bounds are x values. So you might not need to separate that quotient into a product as I've done, but I do think that it can help if we do that to see that here we have a function, and here we have something that looks like, or is in this case, exactly the derivative of that function. So remember, when we're doing substitution, we need to make a substitution not just for u, but also for its derivative. So let's let u be the inverse sine of x, and then my derivative, du dx, would be 1 over the square root of 1 minus x squared. When we separate the differential, I'm going to skip some steps here. When we separate the differential, we multiply both sides by dx. So we get du is equal to the square root of, 1 over the square root of 1 minus x squared. And now we can actually make those substitutions. So now we're going to come back up here. We're going to make the substitutions. And this integral is going to become equal to u. Now this whole thing, notice right here, this whole thing is du. And this was u. So when I'm making these substitutions, I didn't even have to do any kind of manipulation. I can make the direct substitution. So this is u du, and now I can find the integral, because now I have, this is just u to the first. Now I can just apply the power rule. I have an integral in terms of u that is from my basic integration strategies, and I can find that integral. Now, let's talk for a second about these bounds, though. So remember that the bounds were x equals 0 and x equals 1/2. Now, I'm going to show you how to use our new strategy where we replace the bounds with the values of u at those x values, rather than going back in terms of x in the end. But you can follow this whole process just like we've been doing with substitution, and then in the end just evaluate the definite integral across the bounds. But I want to just show you that new strategy here, where we say, okay, well, if x equals 0, then what would u be there? Well, u would be the inverse sine of 0. So when x equals 0, u is 0 because the inverse sine of 0 is 0. So I can change the bounds and make this in terms of u. I'll write it in red so we can see it over there. Actually, no, let's write it in black, but we'll highlight it. I'm trying to decide what colors to use here. So this is u equals 0, and we will highlight that because I've changed the bounds. Whoops, I didn't grab my highlighter. I stayed on my black line right there. Let's undo that. So we'll highlight. Okay, now let's also change the upper bound. So when x is 1/2, what would u be? Well, u would be the inverse sine of 1/2. And so we're saying, okay, well, what on that restricted domain for the inverse sine, what angle has a sine of 1/2? Well, that would have to be pi over 6. So we'll change that bound to u equals pi over 6. Now again, what we're doing here is we're saving ourselves some time in the end. We won't have to go back in terms of x. So let's keep going. I'm trying to keep this all on the screen. You can see my second example popping up there too. Let's keep going. So now we're going to go ahead and integrate. This is going to become, since it was u to the first, integration rules, that becomes u squared over 2. And we're evaluating it from u equals 0 to u equals pi over 6. Now, I do like to show all the steps when I'm doing this, and I will write my u equals 0 and u equals pi over 6 so that I can remember I am all in terms of u. This whole integral is in terms of u. I don't have to go back now in terms, even the bounds. I don't have to go back in terms of x like we would if we were computing an indefinite integral. I just go right in and I'm going to actually compute u squared over 2. I'm going to compute it across the bounds from 0 to pi over 6. So this is going to become pi over 6 squared over 2 minus, well, 0 squared over 2, of course, is just 0. And then pi squared over 36 divided by 2. So that's pi squared over 36 times 1/2. So we get pi squared over 72 as my final answer. Now, again, I'll just kind of make a little note. There are two ways to do this guy. We could have, so right here where I switched the bounds, if I didn't want to switch the bounds right there, I could have gone back in terms of x. I could have substituted in my inverse sine of x for u, and I could have left my bounds x equals 0 to x equals 1/2 and done it that way. We would get the exact same answer. This just allows us to do substitution across definite integrals where we also change the bounds and then plug it in. Okay, let's try another one. Let's see, how many can we get in this video? Maybe we'll get 3 examples in. Okay, so we come across another one, and we're looking at this, and we're saying, okay, what should my u be here? What could my u be? And I'm thinking, let's let our u be that denominator, because remember, if we think about it, and we rewrote this integral, it would be that denominator to the negative first, right, in parentheses. So I'm thinking, well, that's a good option. Let's see if it'll work. See if I can come up with the substitutions here. So my du dx is going to be the derivative of 3 is 0, and then 2e to the x. Multiply both sides by dx. And again, I'm starting to shortcut a little bit of the work with the substitutions as we do more and more examples here. And look at that. That's pretty close to what I have up here. I'm going to go ahead and just rewrite this. And again, you might not need to do this step, but I like to show all the steps on my videos. And then you guys can, as you get more and more comfortable, and as I do more and more examples, we'll skip more steps. So we get 1 over 3 plus 2e to the x, and we've got e to the x times e to the x dx. There's a times there. Times e to the x dx. And so again, I'm looking at that and I'm thinking, okay, I can almost make my substitutions because this piece right here is u, so it'll become 1 over u. This piece right here is almost my du, but I've got that 2 right there. So I'll go ahead and divide both sides over here by 2 so that 1/2 du equals e to the x dx. And then this is 1/2 du when I make the substitutions. Now, we also have those bounds, and so we'll deal with those bounds in just a second. So let's start the substitutions. And we're going to get, this is going to become the integral of 1 over u. This is 1/2 du. And then this was x equals 0. So let's figure out, instead of leaving it as x equals 0, let's figure out what would be the corresponding u's here so that I can leave everything in terms of u and then not have to go back in terms of x in the end. So if x, and I'll show the work over here, sometimes we can do this in our head, but I'll show the work over here. If x equals 0, then u would be, well, it's 3 plus, so it's 3 plus 2e to the 0, so that would be 5. And if x equals the natural log of 4, then u would be 3 plus 2e to the natural log of 4. And so that's going to be, let's see, 3, so I'm going to go down below, so I'll have some space over there. So this is going to be 3 plus 2 times, well, e to the natural log of 4 is just 4, so 2 times 4. So this ends up being 3 plus 8, which is 11. So this is u equals, so again, switching the bounds, so I don't have to go back in terms of x. This is u equals 5 to u equals 11. And then we'll go ahead and continue our integration. So this now is, I can actually pull that 1/2 out. Remember with constants, it doesn't matter if you leave them in the integral or not. It's just a constant multiple. Sometimes I think it's just visually easier to see if we pull the constant out, what the integration formula is that we're going to apply or utilize. And in this case, the integral of 1 over u is the natural log of the absolute value of u. So we still have that constant multiple, and it's 1/2 the natural log of the absolute value of u. And we're evaluating it across the bounds from u equals 5 to u equals 11. Now, again, I changed the bounds, so I don't have to go back in terms of x. If I had not changed the bounds, if I'd left my bounds in terms of x, then I would just substitute my u equals 3 plus 2 e to the x in, and then I would evaluate it across the x bounds. But this is the little shortcut. If we do this work like we did over here, if I do that work first, then when I evaluate it, I just plug in my u values because I already know what u is at those bounds. So u equals 11, so 1/2 the natural log of, well, the absolute value of 11 is just 11. So I'm going to drop the absolute value as I'm doing the calculation here, natural log of 5. So I plug in using that fundamental theorem of calculus, plug in my bounds here, take the difference, and that answer is fine. And I do want exact answers, as does your homework platform. But here I would say, there's a little bit, might as well talk about some rules of logs real quick, because there is a little bit that we could do here, because this guy, we've got a subtraction, we've got those 1/2. We could actually use some rules of logs. And if we remember, rules of logs are so handy, they come in all the time. So if we use some rules of logs here, this becomes the natural log of 11 to the 1/2 minus the natural log of 5 to the 1/2. And then the subtraction, when we're taking two logarithms and we're subtracting of the same base, two logarithms of the same base, and we're subtracting, we can make it a quotient. So this is actually the natural log of 11 to the 1/2 over 5 to the 1/2, and the 1/2 power is a square root, so we could even write this as the natural log of the square root of 11/5. And that is kind of just a nice way to end that example, because we've got some rules of logs that condense that answer down into one nice compact log that would be easy to now plug in. I mean, the other way would have been pretty easy to plug into a calculator too, but we could plug it into a calculator and get an approximation at that point. Okay, let's look at one more example. Okay, so here we've got the integral from 0 to 1 of 8x over 1 plus x to the 4th dx. So it's a definite integral, and it's not one of my basic integrals. So trying to think about what should be my substitution here. What could I use as my u? Now, I want to show this one where we might, let's just pick, kind of like we did in the last one. Let's just pick the denominator and think about if that works. So if u equals 1 plus x to the 4th, when I take the derivative, du dx, I get 4x to the 3rd, and then du is 4x to the 3rd dx when I separate the differential. And I notice up here that I only have x to the 1st. Like, this isn't going to work because I'm not going to be able to make this substitution. And so, and I have to be careful, right? Like, I mean, you might think, well, I could do some manipulation. I could divide by x squared over here, or 4x squared, right? Like, I could think about like, okay, well, I could manipulate like that. And then I've got just x dx, and I could make that substitution. And there's, there is some algebra there that does make that substitution. The problem is then we would be replacing dx with du over 4x squared. That's one problem. The other problem is when I divide by a variable, I have to be careful that I'm not creating division by zero, because mathematically division by zero is not an operation that's defined. It's undefined. And so right here, when I divided by that variable, we have to be careful of this in all contexts when we're doing substitution. There are some programs and some videos I've seen out there on the internet where the strategy is to just solve for dx when we're actually making these substitutions. And while sometimes that's okay, it comes with its own set of problems. And so I'm going to caution you away from doing that, away from that type of a manipulation, because you can only do that manipulation if you can guarantee that your x value, or whatever you're dividing by, isn't going to create division by zero. And in this case, notice that x in our bounds actually is equal to 0, and it's equal to 1. And so this, all in all, this is not legal mathematically, and this substitution doesn't work. So, what are we going to do? Well, we're going to try something else, right? If the substitution that you pick doesn't work, don't worry, just try something else. Like that is the process of working with integrals. Sometimes we have to try something and it'll work, and sometimes we have to get to a place where we say, hey, that is not going to work, and I need to go back and try something else. And that is just our process with integration. It's, in some ways there's some trial and error involved, and the more substitution you do, the quicker you're going to be able to see what the appropriate substitution should be. So do lots and lots of substitution problems. Do lots of integration to learn integration. Okay, so back to the example at hand. I went on a tangent right there. Let's think about what we could do. And I'm looking at this problem. And again, I'm going to go ahead and rewrite it a little, because I think the visual might help us see it a little bit better. I've got 1 plus, I have x to the 4th right there, but that is a perfect square. And, I'm thinking in my mind about the inverse tangent. And so, the inverse tangent, the integral of 1 over 1 plus x squared dx is equal to the inverse tangent. And so that's what I'm thinking of in my mind as I'm looking at this denominator, that's kind of like an inverse tangent. Now, I also have the 8x out here. While we're at it, let's pull that 8 out here. So I don't have to rewrite it again. And x dx. And this is, again, I'll leave the bounds in terms of x on this one, and then we can come back in the end. Once we've made the substitution, we can switch the bounds. So I'm looking at this now and I'm thinking, I see another alternative for my substitution. I'm thinking, what if my u was this guy that's inside the square there, so that my du becomes 2x, it's du over dx, and then we separate the differential, so we'll multiply by dx there. So du is 2x dx, and I'm thinking, okay, I'm starting to get somewhere here, because this I can substitute u in right there for the x squared, and this is almost du. I can almost make the substitution here. I just need to divide by 2, so I get 1/2 du. So what I have left in the integral there, the x and the dx, is actually 1/2 du, and now I can make the substitutions. And so while the original substitution we had thought about, taking the whole denominator didn't work, thinking of this actually in terms of an integral I know, that inverse tangent, and rewriting it a little bit gives us another alternative for the substitution that works. So this becomes 1 over 1 plus u squared, and then this is 1/2 du when I make the substitutions. Now I'm going to go ahead and while we're at it, I'm going to think about making those substitutions while making all my substitutions, I'm going to substitute on the bounds too. So if x equals 0, then u is just 0 squared or 0. And if x equals 1, then u equals 1 squared or 1. And so I can make those substitutions. So this is u equals 0 and u equals 1. And now I can, let's go ahead and we'll pull out that 1/2 as well. So when we pull the 1/2 out, we get 8 over 2. And then this is just the integral of 1 over 1 plus u squared du from u equals 0 to u equals 1. So we get 4 times the inverse tangent of u, and we're evaluating from u equals 0 to u equals 1. And now I just evaluate that. So I get 4 times the inverse tangent of 1 minus 4 times the inverse tangent of 0. And inverse tangent of 1 is pi over 4. The tangent of pi over 4 is 1. Kind of thinking in the other direction if you want to think about where I came up with that quickly. And the inverse tangent of 0 is 0. And so my answer here ends up being pi. And I know that was a little bit of a longer video, but I wanted to get through all those examples and talk about all those things. So please practice with substitution. Remember, if you're working with a definite integral, you can also change your bounds, which makes computation of those definite integrals nice because you don't have to go back in terms of x. But if you like going back in terms of x, you can do that too.